Welcome back to Asymptotics and Perturbation Methods. Today we have the pleasure of doing a nonlinear problem. That is not the sort of thing we've been doing very much of this semester. We mostly focus on linear equations as little case studies, little models that we can handle pretty easily. But today I want to show you some of the wild and woolly things that can happen when we allow our differential equations to become nonlinear. So we're going to use some new techniques. If you've taken a nonlinear dynamics course, you will have seen some of these ideas called phase plane analysis. But we're going to be using phase plane in a way that we don't often use in dynamical systems to help us understand these singularly perturbed differential equations that we've been focusing on that have layers in them, boundary layers or internal layers. So, all right. This lecture actually has a little story behind it. The first time I gave it, I was following closely from Mark Holmes' book, Introduction to Perturbation Methods, and did things his way. But when I looked at it from my perspective as a nonlinear dynamicist, I found that I was getting a little bit confused about some of the claims he was making. And one of my students in that first attempt at this problem found something that seems to be wrong in Professor Holmes' book. So I want to discuss that. And then, as I mentioned this in subsequent years, another student actually confirmed that there really was an error in Holmes' analysis. So I think it's a pretty instructive example. I don't claim that we've solved it totally correctly. These problems are tricky. And so there may be errors in what I'm about to show you too. So be on your guard, be skeptical. But anyway, it's a case study of how tricky these nonlinear questions can be. All right, so let's see here. I'll share my screen. Right, so we're at lecture 16, and as I say, we're going to talk about a nonlinear boundary value problem. So you can read about it in Mark Holmes' book, Intro to Perturbation Methods. The copy of it that I have has seen a lot of good use. There it is. My version is the 1995 version, but there's at least an edition out as of 2013, so you may find different page numbers if you look at the latest versions. Anyway, so in the old version, it's section 2.4, page 68 to 73. All right, so here's the, oh, by the way, so before we get into the analysis, I just want to mention that Holmes uses this as an example of a problem that has another kind of interior layer. We talked in I think it was just the last lecture, about corner layers, which is one kind of interior layer. Here we're going to talk about a different kind, which Holmes calls a shock, or a shock solution, or a shock layer. You may have heard of shock waves in connection with aerodynamics or fluid dynamics. Anyway, so this is a kind of a model case of a shock. So here's our little nonlinear system. We've got, as usual, epsilon y double prime. So that highest derivative will be lost if we formally set epsilon to 0. But then the new wrinkle is we've got a nonlinear term sitting right here, y times y prime. Right, that's quadratic in y, and so that's not linear. This term is linear, but anyway, so we got a nonlinear differential equation now. And so that means that the usual techniques of linear algebra will not work. We don't have a superposition of, linear combinations of solutions aren't necessarily solutions anymore. Everything's really different with nonlinear problems. We don't have any explicit x dependence though. So you could think of it as, in some ways we had that complication in our earlier work with linear problems. We had variable coefficients that depended on the independent variable x. We're not having that here. Okay. Anyway, we're going to study this on the interval from 0 to 1. We've got our usual small parameter epsilon, positive. And the boundary conditions that Professor Holmes considers are these: y at 0 is 1, and y at the other end, y at 1 is -1. All right, so there's our problem. Now, as I mentioned, the yy prime is a nonlinear term. And so the first difficulty we face when you have a nonlinear question like this, to try to understand what's happening, is that unlike in the linear case, which we discussed at some length in previous lectures, where we had, you see like here, epsilon y double prime plus a variable coefficient, a of x y prime, plus another coefficient, b of x times y. There, y is appearing linearly and all its derivatives linearly. There's a theory for that case, for where the boundary layers will be. Right, we discussed that. How do we know if the layer is on the left or the right, or if there will be an interior layer? Unlike in that case, when we have the nonlinear boundary value problems, we don't have any such theory. So we don't really even know where to look for layers in this situation. So what to do? Well, of course, one thing you could do is just say, well, I don't know, maybe there's a layer at 0 and try that and see if it works. You know, see if you can get a solution to match. Do an inner and an outer, try to match them. If everything works, then okay. So you could just take that approach. Just try layers at every conceivable place, at 0, at 1, at some arbitrary point in the middle, x0. See if you can solve the problem. That would be very close to the approach that Mark Holmes uses in his book. And so I'll come back to that and we'll discuss it later. But you know, it can be a lot of work to try many things that may not pan out. Also, there's no guarantee that there's only just these 3 possibilities. You could have maybe 2 layers on the inside, or a layer at one end and one in the middle, or who knows what. There are nonlinear problems that do crazy things like that. So it's kind of scary to figure out what's going on. By the way, if you ask a Mathematica to solve this problem, it doesn't get very far. I tried it this morning, and so like, don't assume that computers will solve your problems for you. This is still something where human ingenuity is required. So, all right, so the approach I want to take, which is not in Holmes' book, but which, you know, is not original to me, plenty of people know this approach, is to use techniques of nonlinear dynamics. So let's approach this problem as if it were a phase plane problem. And so in doing that, I'm going to think of the independent variable x as being like time, because that's sort of the customary picture in dynamical systems. That things are evolving in time. I might even lapse into calling it t, although formally it's x. But so if you take this point of view, then you would think of the dependent variable y, like if I imagine it as a displacement of a mechanical system, then y prime would be the rate of change of y with respect to time. That would be like a velocity, right? So think of y prime, if you want, as a velocity, or maybe more specifically, the velocity of this y variable. And then it's going to be convenient to introduce another variable, z, which is y prime. The reason for that is because I've got this second derivative in the problem. We had an epsilon y double prime term. So it very naturally lends itself to writing a differential equation for z prime, which would be y double prime, is, according to our differential equation, if you solve for y double prime, that comes out to be 1 over epsilon y prime minus y, right? That was the ODE. But now, in terms of our new variable z, that can be re-expressed as 1 over epsilon times y z minus y. And then you could factor out the y, and you get this little expression. So the point is that we can write y prime and z prime just in terms of y and z. That's equivalent to our differential equation. We haven't done anything here, we're just rewriting the problem. But what's cool about this way of writing it is that it has a very geometric interpretation. If you think of y and z as points in a plane, sorry, y comma z as a point in the plane, the yz plane, then what this is telling you is that there's a vector field on that plane. At each point yz, you have a y prime z prime that tells you which direction to move instantaneously from that point. So I'll interpret the differential equation from now on, for much of the time, as a velocity vector field on this yz plane that in this context, we would call the phase plane. So I don't know if you guys have taken nonlinear dynamics. I know some people have, maybe some have not. Does anyone want me to explain a little more what I'm going to illustrate this, but you want to ask any questions at the outset here about what we're talking about with the vector field or anything else? Okay. All right, so maybe that's familiar. Anyway, I think that's as much as I've written out. And so from now on, let's start writing. Okay, so how do we do phase plane analysis is our first question. We've got this vector field, now what? Well, let's draw a picture. This part of the analysis becomes very visual, as opposed to what we've been doing throughout the course, which has been extremely analytic. We can actually draw some pictures now. So let's see, what should I do? Maybe I'm thinking I want to use different colors for the different colors for the axes of my plane and various vectors that I'm going to be drawing and trajectories in the plane. So maybe I'll use blue for the XY axes here, or I mean YZ. All right, so this is going to be Y. There's Z. And now let's write off to the, well, we got the equations above, so we can think about them. What I want to do is sketch the vectors in the YZ plane. And so we can just sort of march around. I mean, you might be noticing if you stare at this differential equation, it's kind of begging to look at what happens when Z equals 1. And so let's investigate what happens there. How about if I mark this off as right here, that's 1. So what happens when Z equals 1? If Z equals 1, you can see that we get Z prime. It's going to be 0 for all values of Y. So what is that? That tells us that the vectors at each point, as long as we're on the line where Z equals 1, those vectors are going to have no Z component. So they're going to be horizontal vectors. Now, which way are they pointing? Well, you can see from the differential equation that Y prime is Z. So if Z is positive, Y prime is positive, which means that this vector is going to be pointing to the right, so that Y prime is positive. Which you could think of as like some abstract, if you imagine an abstract point starting here and think of the arrow as giving its velocity in this YZ space, it says that if you're here, you will move instantaneously to the right. But what's interesting is that when you're on Z equals 1, that's true no matter, I mean, all those points on that line have the same property. The vector field is always to the right. It's actually getting longer, right, isn't it, as Y gets larger? So maybe I should be a little more precise about this diagram. Since Y prime, oh no, that's not right. Since Y prime is just Z, Y prime is just going to be equal 1 at all points there. So they're all the same length, aren't they? They're all length 1. But anyway, what you can see from this picture is that something really simple is happening when Z equals 1. We have what in the jargon would be called an invariant line. If you start on this line, you'll just stay there forever. Okay, so that's one nice feature of our phase portrait, as it's called, this picture of all the arrows in the YZ plane. But we can also observe other things, which is that when Y equals 0, So on the line y equals 0, in other words, on the z-axis, also have z prime is 0, right? As you can see from this equation. If y is 0, z prime will be 0. So again, we're going to get vectors that are perfectly horizontal. So let me sketch some of those in. Actually, though, y prime becomes negative when z is negative. So down here, we would go this way horizontally. Am I doing that right? I think so. And the y, let's see, and y prime is proportional to z itself, so they get longer. Oops. Okay, so there's some information. Now, other things we could observe is that when, like, let's look at this first equation. When y prime, it says y prime is z. So if z is 0, meaning we're on the y-axis, then our vectors have a y prime equals 0, meaning they're vertical. So we have vectors like this on the y-axis. I think I did that right. Now, which way are they going? So z prime, let's see. How do I figure out which way to put the arrows? I look here, and I observe that if y is positive, this term is positive. If z is, I mean, here z is less than 1 because we're actually at z equals 0 on here. So we're just getting 1 over epsilon times negative y. So these vectors are going to be going like so. They're going down over here and up over here. And so you can keep going like this and filling in arrows in various parts of the picture. And you'll see that over here, they look sort of like this, and then they go up. Over here, they're coming down and moving to the right. In this part of the picture, they swirl this way, and this way, and this way. You can see actually at the origin, when y and z are both 0, y prime and z prime are both 0. So there will be a point of rest, so-called fixed point or equilibrium point at the origin. So you're getting an idea of how things move in this plane. Is there any question about anything I've done so far? All right, so let's try to sketch a typical trajectory. I'm going to redraw the picture down here. All right, so here we are, y and z. It's convenient to put in that invariant line immediately. At this point. So I claim that what's going to happen if I sort of connect the dots, well, or follow the arrows, is that my picture will look like, I don't know, we could sort of integrate by hand and just watch what will happen. If I start here, say, I'll follow this arrow, I'll go through the axis horizontally, I'll start coming up. Typical trajectory will look like that. I'll prove momentarily that if I start near the origin, my trajectories go sideways this way, then down vertically, then they come around, and they actually make closed loops. That can be proven that they really do close, they don't spiral. In fact, the shapes, that follows from a symmetry property that whatever the shape is on this side, of the z-axis, you can take the mirror image of that shape, and then that will be the resulting picture on the other side. So the whole thing has bilateral symmetry, though I didn't draw it very well. And that's basically it. I mean, those are what the typical trajectories look like in this plane. Now, one thing maybe I should say, if you haven't thought about phase plane analysis before, is that these trajectories can never cross. You know, that would violate uniqueness of solutions to differential equations. So the trajectories all stay away from each other. Anyway, that's our basic picture. And so that gives us a lot of information. Let me sketch it a little cleaner down here. We've got something like, you know, qualitatively like this, and then these kind of shapes. And up here, stuff that looks like that. So, all right, now let's go back to trying to understand what our question was. The problem was we were studying epsilon y double prime. Let me write it down again. Is yy prime minus y, or in our phase plane way of thinking about it, it was y prime is z and z prime is 1 over epsilon y times z minus 1. But now let's think about the boundary conditions a little bit, because, I mean, this is the part that's not so familiar to those of us from a dynamical systems culture. What are these boundary, how do they appear in the picture? So the boundary conditions on this were what? We had y at 0 is 1, and y at 1 is negative 1. So what does that mean? I mean, that's like saying, if, again, thinking dynamically, that's like saying at time 0, I tell you where y is. Here, I think it is convenient to think of it as time. At t equals 0, y lives somewhere on the line y equals 1, or not just y. I should say it this way, that the point yz, my starting point in the phase plane, yz lives on that line y equals 1. So what I'm trying to say is, visually, it's like this. Draw the line y equals 1. Let's say it's here. And then, you know, interpreting in the same way, this condition, y at 1 equals negative 1, says that at time 1, meaning after we've traveled for 1 unit of time, exactly 1 unit of time, we have to end up somewhere on the line y equals negative 1. So draw that line. That would be trying to make it about symmetrical. That'd be sort of, whoops, something like this. So this is y equals negative 1. And so our question is there some way to start somewhere on this line? Like, let me indicate a possible candidate. Could I start, I don't know, like let's say here, where that trajectory is intersecting the line. If I start there, will it work out that by following the trajectory, that is solving the differential equation, I will hit this line precisely after 1 unit of time. Notice I might even have a second chance. Maybe I could go like this, come around, skip this chance, and hit the line here. That might work too. I mean, there seem like there are some possibilities, but it all has to be done very delicately. You have to last exactly 1 unit of time. I mean, surely this will start here, go around, and hit this line, but it won't have taken the right amount of time. That's the issue. So that's kind of, in geometrical terms, what we're looking for. We're asking for a given epsilon, is there an initial condition in this space somewhere on this line somewhere with the right property that it hits this line after exactly 1 unit of time? So we can immediately see some things. There's no hope for a trajectory up here, right? A trajectory up here is hopeless because if I start here, as time progresses, I'm going this way. And I'm never going to come back to hit the line y equals -1. So these trajectories are ruled out. Or let's put it this way. These initial conditions that have what? Z at time 0 greater than 1 are ruled out. They can't possibly work. Does that make sense? So we can and also, you could even see there's no point considering initial conditions here on this invariant line, because those guys are just destined to go out this direction. They are never going to hit the line y equals -1 either. So I think I could say, I suppose I could start over here, but no, but that wouldn't then start at this point. I have to start on the line y equals 1. Yeah, so we can see that you can actually say those are all ruled out, greater than or equal to 1. No hope for them. So we can restrict attention to these trajectories that start down here somewhere, here or whatever. Notice, by the way, that you have to have a trajectory that's big enough that it actually intersects this line. Like something like this is also, there's no point looking at these because they don't even hit the line. So they have to be big enough to intersect. But there are plenty of them because the phase portrait shows that if I start close enough to the line z equals 1, I'll actually go out kind of far. And then come back in like that. They get all packed in kind of near z equals 1. So the whole plane is filled, literally foliated in the language of geometry. The plane will be foliated with these trajectories. Okay, so anyway, that's the picture. Now, how do we start doing some math, you might say? This is math. This is geometry. This is qualitative math, but it's giving us a lot of insight. Okay. So what did we conclude so far? We know that the only hope is to have z0 has to be less than 1. All right. So we are looking for the right choice of z0 when y0 satisfies its condition that y of 0 is 1. So you can think of it that way. Now, by the way, what is z0? Like in terms of the original problem, z0 means y prime of 0, which is interesting because that, like now taking a more standard point of view, you could think of it this way. that if I just think of y as a function of t, and I said I'm going to start at, actually, let me put down some -2. So let's suppose I start here. This is time 0. We've chosen our initial condition to be y of 0 is 1, so we've got that covered. We start there. And then what's supposed to happen? We're supposed to end up at time 1 we're supposed to end up down here. Right? We want it to be that y at time 1 is -1, if I've remembered my boundary conditions correctly. Yes. So the game is start at this point, and now this is the part that's kind of cool. I say what we're doing is we're looking for the right choice of y prime of 0. Meaning, think about it as like I need a launch slope. If I pick the right y prime of 0, once I pick that, you could imagine doing this in a computer, a numerical method even. Choose the right y prime of 0. What happens then? Well, after that, you're carried along by the differential equation. So after that, you just follow the rule that epsilon y double prime is y prime minus y. Right? So knowing the y, like here you are at some place, you know your y, you know your slope, that dictates y double prime, that tells you how much to curve. So you can basically just integrate forward, and what will happen is you'll get something. I mean, let me just try to sketch one in. It might look, I don't know, say it looks like that. So that was close, right? We almost hit. So I didn't quite hit because this point is just a little bit off. So that means I might have to try a slightly different y prime of 0. And so in numerical methods, this kind of way I'm reasoning is called a shooting method, because it's almost like ballistics. Like you're operating a cannon and you're trying to hit a target. So if you tilt the cannon just right and fire, you're trying to shoot until you bang, hit this point. Not following a parabolic trajectory. It's not a real cannon shot. It's following the differential equations rule, which is different from the law of gravity. Okay, so that's it. That's what we're trying to do. And so let me show you some examples of what this actually looks like in the computer. I generated some pictures here. So this is really what the phase plane looks like. These are ancient yellowed pages. I don't even know if you can see them. These are pages from a long time ago. I was solving the equations not in Mathematica, some other software. But so you can see what the trajectories look like. I don't know. Hopefully are these actually visible to you? The lines aren't too thin. You're okay. All right. Yeah. Anyway, so you can see they're qualitatively like what I said. They're doing this. They're going around. They're getting all packed up. These guys are going up like that. But here's the interesting part where you can think of it as shooting. If I start the trajectories at y of 0 is 1, I vary y prime of 0 to try to achieve y at 1 equals -1. I chose 3 values for y prime at 0, 0.2, 0.8, and 0.99. And here were the results. So notice I'm starting over here at y equals 1. This is my y-z plane. I don't know if those are visible. This is y. This is z. So I started them all on the same vertical line, and they all make their merry way around. But who lands in the right place at the right time? Well, here's actually the y of t picture. You can sort of see they look, well, this one started, they all started at -1. They get launched at different angles. and they have different fates. And this whole thing is sort of making some continuous collection of continuous bundle of outcomes. And if you choose right by the intermediate value theorem, you should be able to find something that works. And there are numerical methods that can do this, but we want to try to think about it now more, go back to the geometry way to convince ourselves that there really is a solution with this type of shape to it. All right, so I think I'll continue with my analysis from there. Is there any questions so far? Okay, so I mentioned that I wanted to prove that all the trajectories were closed curves. I don't know if that's really worth going into. I sort of already sketched it. It's by a symmetry argument. Maybe it's worth just saying briefly. I don't know. Okay, let me just give that argument quickly. So we can prove that all the trajectories that lie below the line z equals 1, that invariant line, are closed curves. So use a symmetry of this particular system. So I'll write it in the phase plane style. The system was y prime is z, and z prime is 1 over epsilon, y times z minus 1. So what is the symmetry I'm referring to? Well, the computer picture's already sort of indicated what it should be. If I switch x to minus x, y to minus y, and z stays the same. So what you could think of this in, if you take the interpretation of x as time, this is like time reversal. Sort of like running the movie backwards, and thinking of y as going to negative y. Then, so this is a mirror on y. Then everything, the differential equation stays the same, because dy by dx, if I change y to minus y and x to minus x, then I have dy by d negative y by d negative x. This is just still dy dx, which is still y prime. And I mean, so what I'm saying is, look at this system of equations. Under this change of variables, the equations stay the same because y prime, what am I trying to say? The equations for this new set of variables are the same as the equations for the original set of variables, because the y prime stays the same, the z stays the same. This equation is still satisfied because z prime would change sign. Why is that? I mean, z prime would change sign under this change of variables because it's now d negative z. So, sorry, z doesn't change under this. We said z goes to minus z. So this would be d of z, but the time variable, we're changing to negative of itself. This becomes, you know, minus z prime. Like I said, it changes sign, but so does the right-hand side of this differential equation, because the z minus 1 has stayed the same, but the y has changed sign according to this. So what I'm claiming is that let's put it this way. If y of x, z of x is a trajectory for the system, then so is negative y of negative x comma, z of negative x, because they satisfy the same ODE. So what that boils down to is, if I have a picture, like I argued earlier, in which some trajectory starts on this z-axis, comes around, and then hits again, think of that as the y of x, z of x part of the trajectory, this part. And then I'm claiming that its mirror image across the z-axis is also a trajectory, but with time running backwards. So that makes the arrow go this way. So anyway, that forms a closed curve. Is there any question about that little symmetry argument? I mean, this is an example of a reversible dynamical system in the jargon. So reversible ODEs often have these closed orbits in them. Okay, so having said that, now notice so far we haven't used any perturbation theory. We have not used the fact that epsilon is small. Or the assumption that epsilon is very close to 0. So let's start using that now to reason what happens in our system. So let's examine this differential equation in light of the smallness of epsilon. It was y prime is z. Z prime is 1 over epsilon, y, z minus 1. So think about this for very small epsilon. What you should observe is that there are 2 time scales, depending on where you are. Again, I'm thinking of x as like time. They're very different, I mean, or x scales if you prefer to think of it that way. So what am I saying? Consider 2 cases. Suppose z minus 1 is order 1. You know, and we're thinking of epsilon still being small. So like imagine z is 2 or 3 or 1.5 or whatever, 0.5. I mean, z, so we're not too close to that invariant line, is what I'm saying. So we're not close to that line z equals 1. If you have that, then when you look at this system up here, think about what's going on in the vector field. If this quantity is order 1, and also let's suppose that y is not 0. So if we have those 2 properties, this term is some order 1 object y. This is some order 1 thing. The point is 1 over epsilon is a gigantic number because epsilon is small. So think of this number as a trillion. So we're saying z prime is a trillion, whereas y prime is some order 1 thing because it's just z, which is close to, you know, sort of in the, there's nothing special about z. Z is slightly, you know, z is anywhere, just not too close to 1. So the point is z prime is much, much bigger than y prime. So if we're in this regime, Z prime is, let's put it this way, is order 1 over epsilon. Which is huge. And that means that we have a huge vertical velocity in the phase plane. And that corresponds to a very rapid variation in Z. With respect to X. So that's all happening as long as Z is not too close to 1. Now, a rapid variation in Z is what we call a layer. Right? This is the dynamical system way of thinking about a layer, that Z is changing very quickly with respect to changes in X. So this is corresponding to some kind of inner region. Some kind of layer. Z changes rapidly with respect to X. Are you with me on that? I mean, I said there's going to be 2 time scales. This corresponds to a time scale. This is stuff happening very fast, probably a time scale of order epsilon, very short times. Or space scales of order epsilon, because it's a layer of thickness epsilon, it's going to turn out to be. So the other possibility, though, is that otherwise, I mean, if you're very close to Z equals 1, namely, if Z minus 1 is just order epsilon, well, then something different is happening, because if you look at the equation, Z prime, which was epsilon y times, wait, did I do that wrong? I'm sorry, I meant y prime. Wait, Z prime, let's try this again. Oops. I meant 1 over epsilon, that's my mistake. 1 over epsilon y Z minus 1 is our equation for Z prime. You can see the issue. If this term is itself order epsilon, it will cancel with this epsilon. And then Z prime will be order 1. So in that case, everything is kind of mild. Z prime is order 1, Y prime is also order 1. It's just Z, but that's going to be some order 1 thing throughout the finite phase plane. So this is a very gentle region. As long as you're away from that invariant line, everything's not changing very rapidly. This is what we would think of as the outer region in geometrical terms. We have gentle variations in Y and Z. Not rapid.
So basically in this situation, the outer region will have the thickness of the inner region from the previous times, because usually the inner region was the one that had the order epsilon, but now the outer region has that.
It's strange, isn't it? Yeah, in the phase plane itself, that's an interesting comment. That's an interesting comment, Maria. Right, so in the phase plane, if I go back and look at, oh, I don't know, say a picture like this, you're right. I think what you said is right. that the outer region corresponds to a thin part of the phase plane near that invariant line. Whereas the inner region, where the variations are rapid, corresponds to a big swath of the phase plane. But that's because the variable x is not being shown in this picture. This is the YZ plane. X is it's rapid variations with respect to x in the layer, and you're not seeing, I mean, what's really happening is that this part of the picture is very fast. You zip around on that part, and up here, it's very slow. This stuff, you go blindingly fast on this part of the trajectory. So anyway, everything that you asked is right, but it's not, it shouldn't be surprising. It's because the x is invisible in this representation. Just like time is not shown on a phase plane.
It makes sense.
Yeah, okay, good. All right, so, but this gives a lot of insight thinking this way, even though we're just kind of doing qualitative reasoning. So let me summarize what we've got. It just came out really from your question, but actually, maybe I'll copy this earlier picture I drew. Let's see if I can do that. This picture, this is a pretty good picture. Let me copy this and drag it down. Let's see if this works. I'm going to say duplicate. There it is. Now come with me. This is something you can't do on a blackboard. Okay. Hello. Let's leave it there. Okay, I'm going to erase some stuff that we don't need right now. I don't need this comment anymore. All right, so that's a rough sketch of our picture. Actually, I don't have so much room to draw. What I wanted to, well, let me think of it this way. Actually, let me just sketch it cleaner. Well, I don't know. What am I trying to do? Let me focus on a few points of interest. Suppose I start where I've just indicated with that dot. I'm going to call that point. Maybe I'll make this a little bigger. I want this whole thing to be bigger. There. Ah. Okay. So I want to call this point A. Right there where I'm starting. Then I'm going to think about what happens when I get down to here. We'll call this location B. And then I'm going to come around till I hit, let's suppose when I hit the line at this location. Remember, I'm trying to hit that line y equals -1 at precisely after 1 unit of time. So let's call that place C. I don't know if that's visible. That's point C. There's A, B, and C. So let's try to translate this into a Y versus T picture. I mean, what does this tell us, what we've drawn here? Actually, let me call it X to stick with the notation we've been using. And let's be interested in the place where x equals 1. All right, so what's our picture telling us? At A, well, we know we start at a y of 1. This is the point A, right here. And observe from the picture that it looks like we might have a candidate solution with a y of 1, and its z is slightly less than z equals 1, because we know this line is z equals 1. So our slope, I mean, this number is something a little bit less than 1, so we should come up with a slope from here that's approximately a slope of 1. But then what happens? Well, notice that we're getting farther away from the line. And at some point we go through here. That's where z equals 0. That means y prime is 0. So we're actually getting something that looks, its slope is becoming flat, right? The vertical direction in this picture tells me, the vertical direction in this picture is telling me the slope in this picture. And so I'm getting something like that. Now, what's happening at point B? So here at B, I mean, let's trace this out. My slope has become, okay, my slope is 0. Now my slope is becoming more and more negative until it becomes extremely negative. So what's actually happening is something like this. Slope is becoming more and more negative, very negative. Then once I cross this point, my slope is not as negative. It's still negative, but it's becoming less and less negative until it becomes 0. Where it's now become 0. And then it becomes positive when I go through here until I hit this point at C. So my slope has now become positive and starting to do this. And actually, as I start coming in through here, my slope should be very close to negative. My slope should be close to 1, right? Because I'm close to the invariant line, z equals 1. So I haven't drawn it too well. Let me try this again. This should have a slope of 1 over here, about, and then connect. So qualitatively, we're looking for a y versus x that's going to look like that. I mean, that's a plausible solution. That's a solution that could work conceivably. Not proving anything yet, just looking for candidates. Because remember, we don't even have any idea where the layer could be.
Shouldn't y of 1 be
oh, thank you,
negative
thank
1?
you, thank you. Excellent. Absolutely, I've screwed that up. You're right. Very good. Good eye, good work. Right, this is supposed to be -1, isn't it? So it's supposed to hit here. Good, thank you. And this is at time 1 here. Okay, so I'm looking for a solution that looks like that. I think that's a plausible candidate. And so this suggests, I mean, you can sort of see if you use wishful thinking, which is often a good strategy in math, try to make it work. The picture suggests some kind of interior layer halfway across the interval at x0 equals a half. And no layers near A. So in terms of my points A, B, and C, let's see, where is B? B is this place, the steepest slope, and this point is C over here in terms of my earlier picture. So it suggests an interior layer at B near a half. So if you're with me, I want to now revert to standard boundary layer thinking and just construct a solution of this type. But then I want to tell you some surprises after that. Okay, so let me barge ahead with this. Let's just resort to usual thinking about the inner and the outer solution. So our governing equation, going back to the original formulation, was epsilon y double prime is y prime minus y. It's like that. And so the outer solution, which you could get by formally setting epsilon to 0, if I write y equals y0 plus ... ignoring the order epsilon terms, the lowest order in perturbation theory would give me y0 prime minus y0 equals 0, just the right-hand side, ignoring this term. That's at order epsilon. So that's a nice little first-order differential equation. In fact, a very easy one, because you can factor out the y0. Then you have y0 prime minus 1 equals 0. So we either have y0 is the 0 function, or y0 prime is 1, which would tell us that y0 of x is of the form x plus a constant, let's say a. Actually, I think I want to start inserting some pages here because I don't want to go to this next thing yet. Add page. Let's add a few more. Okay. So we've just got this nice little result here. Let's ignore, what are we doing? We're trying to look for something where we think of this as being an outer solution that looks like it's trying to be the straight line y equals x plus a constant. And this one also looks like it wants to be a straight line of the form y equals x plus a constant, just with a different constant. And those constants will be determined by matching them to these boundary conditions here and here. That's the outer region. Then we're going to have to patch that together with whatever is happening in here in the inner region. Okay, so that's the setup that I'm going to just quickly go through. So using the boundary condition on the left, which says y0 on the left at 0 should be 1, that will give me y0 of x on the left is just 1 plus x. And similarly on the right, you'd have y0 on the right. Well, let's see. At 1 is supposed to be -1. So that would tell me y0 on the right as a function of x is x minus 2. So the sketch is that those two together look like this. That goes up. We stop here at 1/2 where we think the layer is. This was at 1. It's going up with a slope of 1. So this point will be 3/2 there. Whereas the other one, which looks like this, has to reach -1. I think my scale is a little bit off, but you know what I'm trying to show. -1 at 1. This point will be, when you calculate it, -3/2. And then I have some kind of, I need an inner region that's going to be a capital Y to join these to match. Right, this one is my Y right of X, and this one is my Y left of X. I guess I was using subscripts earlier, or superscripts, sorry. L up there and right up there. Okay, so now we have to do the inner region. And let's quickly do that. Actually, this takes a little, I may have to go over slightly, but if you do a dominant balance argument on it, we can convince ourselves this layer has to have a thickness of epsilon. So to deal with the inner region, let's let big Y, sorry, let's first define big X. To be X minus 1/2 over delta. And then my Y prime, which means, I'll define it to mean dy by d big X. So slightly abusing notation here. Oh, actually, it's, yeah, all right. So this will give me, and this would say that Y prime, with respect to its argument, little x, is 1 over delta Y prime with respect to its argument. So Y double prime will be 1 over delta squared, Y double prime. And so my governing equation would become epsilon Y double prime over delta squared is YY prime. Sorry, I'm skipping steps. Y, it's big Y. Then I'm supposed to do Y, little y prime, that's Y prime over delta minus 1. So this is my ODE in these coordinates. And you can see from a dominant balance matching these two, the distinguished limit turns out to be epsilon. Delta is epsilon. So if I do that, then the equation comes down to Y double prime is Y prime minus epsilon Y. So that's my inner equation. And at lowest order, so now if I solve this, and right, Y equals Y0 plus stuff of order epsilon and higher, then the Y0 satisfies this little equation. Y0 double prime is Y0 prime, which you can recognize both sides are perfect derivatives because this side is dd big X of one half Y0 squared. Right, by using the chain rule on that. So you can integrate once and you get Y0 prime is 1/2 Y0 squared plus a constant. which is interesting because this is telling us the shape of the trajectories in the phase plane. It's telling us that they are parabolas. I mean, because remember, y prime is what we called z. So if I go back to my old pictures, these arcs that I was drawing down here, these are actually parabolic arcs to lowest order. So anyway, there's three choices now for the constant. I mean, if I call the constant capital A, so I have to worry, do I have A less than 0, A equals 0, or A greater than 0? But we can see from our picture, I mean, from the geometric reasoning that we did back here, that the intercept for this parabola is a negative number. It has to be down here on any of the trajectories that have a hope of working. These parabolas are irrelevant. We already decided. So I'm going to argue that this constant, this intercept, has to be negative. And so I'm going to call it something convenient. From the phase plane argument. So let's say that A is, just to make the algebra come out nice, call it negative a half b squared, or for some constant b, to ensure that I get a negative number. That gives me the nice equation y0 prime is 1/2 y0 squared minus this thing I'm calling b squared. And I can separate those variables and integrate. So dy0 over y0 squared minus b squared is 1/2 d big X. And both sides can be integrated. It ends up giving you a tanh, is the nice way to look at it. Y0 of big X is b hyperbolic tangent of some other constant c minus b over 2x. So in the interest of time, let me sort of jump ahead here and just say that if I take this as my inner solution, and then I use the insight that I gained from my phase plane thinking, and look at this picture of what kind of inner solution do I need to be able to match those two straight lines, or also to look like this picture that I've drawn here, where I'm going through 0 when X is a half. So to match onto these straight lines and to go through 0 at X equals a half, when you determine all the constants, the B and the C here, you'll end up getting, so I'm going to skip these steps. You'll get that y0 of X, the inner solution to lowest order, comes out to be minus 3/2 tanh of 3/4 X. So this is after matching and after using that y0 at a half is 0. So we get that nice formula. So officially I'm out of time, but I would like to just finish, and because I only need a few more minutes. So if you'll bear with me, let me just plow ahead. If you can't stay, I totally understand. So feel free to go, and you could watch this on tape afterward. But I'm just going to finish here then. So all right, so there's my y0. And we can also write down the composite solution now that we've got the inner and the outer. So we had y left of X was to lowest order X plus 1. Y right of X to lowest order, I guess I should say asymptotic too. Let me do that. asymptotic to x minus 2, and y of x on the inside asymptotic to minus 3/2 tanh 3 big X over 4. And so when we write out the composite solution, let's suppose we seek y composite on, let's do the left half of the interval first. I mean, there's two halves kind of very naturally. So if we do that half, I mean, we want it on both. We also want it on x between 1/2 and 1 also. But if I just do this part, here, you'll get something like, if you use the outer plus the inner minus the match, on the left half, you have x plus 1, then plus this tanh thing, so minus 3/2 tanh 3/4 of, in the old variables, x minus 1/2 over epsilon is my big X. And then minus the match. The match is 3/2 because, I mean, all these 3/2 are coming from this picture where this point was 3/2 right here. Right, we needed a y value of 3/2 in order to match this tanh thing that's happening in here to this 3/2 at the end of this outer solution. So looking at the, did I call that the right? I mean, yeah, so this is dealing on the left. I have this expression, and when I simplify it, this gives the y composite on the left is asymptotic to x minus 1/2 because this 3/2 and this 1 conspire to make a negative 1/2. So I have x minus 1/2 minus 3/2 tanh of 3/4 x minus 1/2 all over epsilon. So that's my composite solution on the left. And the interesting thing is, if you do it on the right, you'll get the same expression. So it sort of makes sense. This whole equation is odd about the point x equals 1/2. Tanh is an odd function, x is an odd function. This whole thing has odd symmetry about x equals 1/2, y equals 0. Right, I mean, you can sort of see it from the picture. This shape is odd about this point. So there it is. So that's a full solution of the interior layer and the outer and everything all put together. But here's the part I wanted to mention, which is that there are other solutions to this problem. The solution to nonlinear boundary value problems are not necessarily unique, and in this case, they're not. And what's interesting to me is that Professor Holmes in his book implies that it is unique, but he doesn't prove it, and he says he's going to give a plausibility argument. So let's see if I can find that here in my, I want to show you this. Yeah, I can delete this page, and I'll delete this page too. But here's his plausibility argument that turns out to be wrong. It's interesting. He says, imagine that there was a layer near x equals 0. It turns out there can be, but he says, suppose that there was. He wants to argue that something's bad. He says, if you were near x equals 0, it would have to have this kind of shape. Out here we have the outer solution, which we already know looks like this to satisfy this boundary condition over here. So you'd have to have something that's coming down and then would match onto this. And he assumes that the concavity of this inner part is concave up. like that it decays exponentially sort of away from this boundary point. So he says, if near x equals 0, you'd have y prime negative. Well, yeah, it's certainly decreasing. And y double prime positive. That is, he expects it would be concave up if it's like the other example problems that we've done. But then he says that would mean epsilon y double prime would be positive, but this expression is both positive and negative in the layer. Why does he say that? Because y is changing from positive to negative, whereas y prime is staying one sign. It's negative throughout. So he says this whole expression is manifestly two signs in the layer, but this he thinks would only have one sign. And so he doesn't believe that there's a layer near 1. So anyway, he says this is a plausibility argument. I mean, he's careful. He says it should be pointed out these are only plausibility arguments and do not prove anything. But they guide the analysis and suggest that you should look for the layer that we just found in the middle of the region. Okay, and so that's kind of where he leaves it. But it turns out it's not right. Even though it's plausible, it's not right. So this is what some students of mine discovered when we were doing this. I thought, based on phase plane analysis, why couldn't I just kind of, in addition to going slow here, whipping around, and then going slow here, that gives us this type of behavior. Why couldn't we have something that started out fast and then spends all of its slow time on this side? Why couldn't that work? Well, it can. And so Mario Gomes computed that. He showed that the initial slope has to be this number, negative 10.69. He's assuming an epsilon of 1/10. So he computed a layer that works. And it's not symmetric. And he also computed one on this side, where you spend all your time dawdling like this, and then you whip around and end up in the desired line over here. That had to have an initial condition extremely close to 1. But, so you spend all your time going in this outer region, and then you quickly zap down. So he said that should also work. It worked for him numerically. And so I pointed this out to students in, classes in between yours and these first ones. And I just want to share one other thing with you, which is from this next generation of good students. So I'll share my desktop. This guy is a current grad student, but he took the class last year. This is Arnaldo Rodriguez Gonzalez. So last year, he wrote up this nice little analysis where, in Professor Holmes' book, he says if you try to do a layer on either end at 0 or at 1, it won't match. But Arnaldo did it, and it does match. So let's see, I'll just zip through here. He actually shows you can set up a solution with a boundary layer at x equals 0. There's nothing wrong with it. You get the outer solution that you would expect, an x minus 2. You can solve and again get Tanch-like solutions, but he was able to find constants that matched. And he wrote it down, and there it is. And the interesting thing is, I asked him calculate the second derivative. Holmes had argued that it should be concave up, but Arnaldo computes the second derivative is actually negative at the beginning of the layer. So this whole plausibility argument just doesn't work. So anyway, I'll post this in the notes. You can read his paper if you want. But anyway, in the phase plane, Arnaldo computed just what Mario Gomes had also computed, that, this solution has the layer in the middle in the phase plane. But you can also have ones that look like this one in green that start down here, go fast and then slow. Anyway, I belabored the point. But the lesson here is that nonlinear boundary value problems are really tricky, and just blindly looking for layers can be dangerous. You really should use geometry to supplement your thinking. And even then, these problems are tricky. So let this be a warning to you. And they may be so tricky that we may have done something wrong. So please be skeptical and think about this problem for yourself. Okay, thanks for letting me go over time. Okay, so sorry that took so long. Anyone want to ask any questions about anything? I'm 10 minutes over.
Sorry, go ahead, Jackson.
Doesn't that last picture you have imply the existence of one more solution, one where it's kind of the reverse time thing, where you start in the upper part and end in the lower part?
So let's see if I follow you. So you want me to start up
Yeah.
here, but I think I do have one like that.
Oh, okay. Cool.
Yeah, absolutely, we do. You can spend your time here, or you can spend your time here, or you can divide your time between here and here. I mean, these,
Awesome.
remember, are slow. So those are your three choices. You cannot do, I was wondering, could you have more layers, but you can't, because if you, once you come around, once you hit this part, this is really slow. You're going to spend all your time up here. You can't do that twice. That's going to take too long, I think. So I don't think there's any solution that has more than these, than a single layer. But yeah, you can absolutely do this if you want. And that solution then corresponds to something that, you know, back, let's see. I mean, so Arnaldo color coded them. They, I mean, what was interesting is that he could use his methods by writing down the composite solutions for the three cases. He could estimate to lowest order what the initial slope would have to be in order to get these desired solutions. And these, it's a little hard to see. This one ends up having a slope that goes to negative infinity as epsilon goes to 0. That's pretty clear. But these have slopes that are very close to 1, and they differ from 1 by transcendentally small terms. But you can calculate them according to this. They don't make a very good numerical fit, but they're probably the heart of the answer. Anyway, so yeah, I think there are 3 solutions to this problem, not 1.
Cool. Thanks.
Good. Yeah, good question. Was there another question? Maria, you had a question?
Yeah, so I was wondering how do we get the fact that the boundary layer should be at 1/2 from the picture we were drawing? Because it just seemed that, okay, it's symmetric on one and the other side, but then you could just randomly meet that, randomly decide
Right.
that 1/3 to just go down.
I know, I hear you. It's reasonable. I'm not sure I totally believe that part. You might be right. I'm not positive that it is forced to be at 1/2. Professor Holmes gives an argument that it is at 1/2 in his book. He gives a symmetry argument. I sort of, I don't know. That's a good question. You know, given what we've just said about the phase plane picture, why couldn't you spend a certain amount of time here and make the whole thing a little bit asymmetric and maybe spend a little more time here? Is that possible? Oh, no, I don't think it is possible because the nature of this trajectory is that when you land at 1, remember the symmetry of the whole picture. If you start here at at y equals 1, but you have some arbitrary choice of the z, I mean, that's what you're looking for. The orbit that you make by the time you hit at y equals -1, this whole shape has perfect symmetry about the line, the z-axis. So the slow portion of time spent here is exactly the same as the slow portion of time spent here. It has to be, because those trajectories have that symmetry. I think that's right. Do you not agree with that? I don't think there's any way you can avoid this symmetry, and that then forces you to, at the halfway point in your journey, be here, meaning that you go through a slope of 0 exactly at time 1/2. I think
But
that
in
is really
that,
forced.
but in the other two cases, you're spending, well, all the time in one side, but
Ah,
0 on the other side, so there's no
right,
symmetry there, right?
right. But observe where you land. You start at the low point on the line. Remember, there are 2 points where the line crosses the trajectory. There's a high point up here, and there's a low point down here. So if you start at the low point, that's okay. Then you can spend all your time up here on the slow part and end at the high point. But if you start at the high point and come around and end at the high point, then I think you're stuck with the argument I made. I don't know if you know what I'm saying with the high points and the low points.
I get it. It makes sense.
Yeah. I kind of think it is it is correct that there's exactly 3 layers and that the interior layer has to go through x equals a half. I think we could make that a rigorous proof by this geometry. Yeah. But never positive. I don't know. I may be overlooking something, but I think it really does work. Anyway, very tricky stuff. You have access to Holmes's book. That's part of our site license through Springer. So you could look up the whole book and read his analysis if you want to see it. By the way, I have, as a collegial thing, I wrote to him and sent him Arnaldo's paper, but he doesn't seem to respond to email. And my friends at RPI, where he teaches, said, yeah, he often doesn't look at email. So maybe I ought to mail it to him by snail mail. And I mean, I don't know if he's aware of this analysis, but he really should correct the book than in the next printing. And I sympathize as a textbook author myself. I like it when people correct mistakes in my book, which there certainly are some. Okay, so let's quit there. See you later.